I've had a request to go over the material in the notes, and of course here I'm referring to our Dropbox folder, and we've got the set of notes. So we've got the Python files that I've been using in the other videos, and then of course we have all these notes numbered from 1 to 7, and I guess some people have been having some difficulty following one of these sets of notes. So this first one has this real-time state simulations and control. And yes, it is the case that I only included this as a kind of transition from the first part of the course where model development was the emphasis. So in the first part, you did rigorous development of the models that described how the states of the system were changing. So I thought, just to smooth things out before we jump straight into Laplace transforms and so on, to do a little bit of modeling. So that's what this whole section of notes is about, because everyone has their own style of modeling. So I thought there would be quite a disconnect if you went suddenly from modeling into Laplace transform. So that's the purpose of these notes. So let's work through it. And here we are just defining the basic structure, and we are just showing here that the states that we are going to refer to are the states that describe some process, or some entity. So in this case, the entity is this reactor. So the symbol implies some kind of good mixing, and so we have this vessel, and it's a reactor, and we can characterize the state of this reactor by our choice of variables, which may include things like the temperature. If it's a gas phase reactor, then the pressure is another good one. We can talk about or define the total concentration. We can also define the concentrations of various species. So when we refer to the fluid inside this vessel, we can think of the states that describe best we can think of the variables which define the state of this fluid. So that's what we are trying to develop first in this in this description. So here, where we are defining y is a function of time, we are expecting that y would be some vector of states. So it's some vector of variables. And as I've mentioned, those variables may include things like temperatures and pressures and so on. So that's, we hope, fully describing the state of the fluid in this vessel. And furthermore, we recognize that in the model development that you've seen in the first part of the course, that quite often in our engineering models, we will be able to describe the rate of change of the state in terms of the value of the state and some applied control on that system. So the applied control now is different to the state. So the state tells us the characteristics, if you like, of the fluid in here, whereas the control action, things like the flow rate, right? In chemical engineering, most of the time it's about flow rates. That's the one thing we can really manipulate well, right? We can stick a control valve and we can change the flow rate. So that's what we like to do as chemical engineers. Electrical engineers, of course, like to apply different current and voltage and so on. So, and in fact, it's the same thing, right? Current flow, it's they just happen to be controlling the flow of electrons, and in the analogy with them, they are controlling the pressure difference. So the voltage is like the pressure difference for us, right? So we've got we are controlling the flow, and most of the time we are doing it through a flow control. So if we are trying to control the temperature, then we'll change the flow rate of the steam or the cooling water. If we are trying to control the pressure, we'll go and change the gas exit flow rate. If we are trying to control the concentration, we'll change the ratio of the streams at the inlet point and so on. So almost everything that we do involves changing just the flow rate of something, and normally there's a flow line that's going to influence one of those state variables. So if you like, mathematically, that's how we accomplish that. We can talk about changing the states here by changing the flow rates. Of course, that's not the only thing. We can do things like change the degree of agitation, so we can change how fast we are mixing things, and so on. We might also include, we might be pushing down here with a piston or something like that to change the pressure. So there are other things, but most of the time when you see flow control diagrams, and we will look at some just now, you'll see that we are, by the end of the day, accomplishing some control intention through controlling a flow rate. So that's what that U normally means in chemical engineering. There's some flow rate that we are trying to control. And then the Y is there's some state of some entity. And in fact, quite often we just jump straight into deriving these equations, and up to now you've been seeing, we will just dump the accumulation term, steady state, and then we solve it. Now, of course, in control, things are changing in time, and so we are going to carefully preserve our accumulation terms in this course. There was something else. So our entity, when we say these are the states of some entity, it's useful for us to first define what the entity is, right? So I had an email about trying to understand what states were. So you can understand what the states are if first you define what the entity is. So here we say the entity, the thing we are trying to center our control efforts on is this reactor. So the reactor is the thing that we are trying to work on. So once we know that's the reactor, then we can start thinking, well, what characterizes the reactor? What am I trying to do in this reactor? So in the reactor, of course, we are trying to react something. So we then know what sorts of variables are relevant to that. So if we know we are trying to react something, then obviously the reaction rate is what's important here. And the things that influence the reaction rate, of course, most strongly, it's the temperature. Then, of course, we also want to pay careful attention to what we are feeding to that reaction space. So it progresses like that. We cannot just abstractly say, there's a model of something. And so we want to try to understand first, what's our control effort about? It's about this reactor. What goes on in a reactor? Yes, we try to react things, so the reaction rate, and so that cascade of thought, that's what you need to use to really understand state variables and what we are trying to do. So anyway, most of the time you'll see from your mass and energy balances, we'll end up with some system of ordinary differential equations. And mathematically, the moment you write down some system of equations where the equations may be related, right? Y is generally a vector, so you may have y1, y2 up to some yn, and any y there is influenced by any other y. So for example, if one of the y's was temperature, then temperature is, of course, the temperature in the reactor is changing depending on the temperature itself. So because of some current temperature, the reaction rate occurs at a certain value. And so there's a tendency then for the temperature to be changing with time depending on that current reaction rate, which itself depends on the temperature. Now, the reaction rate there, which we've just said affects the temperature, that reaction rate also depends on other things. It also depends, obviously, on the concentration in there. So when we write this equation, if we were writing this in terms of temperature, so in fact, let's just do it here quickly. So we are writing that we've got some system of equations dt. Well, that's one of the variables, and that's equal to some function of, and we know it's going to be a function of the temperature in the reactor itself and of the concentrations of the reacting species there. So let's just call that F1. So we know that we'll have some equation for the temperature like that, And similarly, we can write another equation for the concentration of some component. So this will be some other function, but it will also be a function of the temperature, because, for example, the reaction rate is a function of temperature, and then the rate will also depend on the concentration. And just for example, quite often, if it's a CSTR, for instance, you'll have seen in the reactor fundamentals course that quite often for the CSTR, you'll get a form that looks like this. So the rate of change of the concentration, and then minus RA, R, or RI. Well, then I should say strictly that that's normally the rate of formation. And of course that is equal to, here we can just expand out for RI. So it might be some kinetic rate constant multiplied with the concentration of A and raised to some reaction order, of course. And this kinetic rate constant is a strong function of temperature. Remember, there's some Arrhenius relationship there, and so that will be the form of the equation. So we are saying all this now because we can see then that in that general form, you've got a vector. We can summarize all this with a vector of equations in this form. So that's what's behind this kind of representation, right? If you go ahead and write your energy balance and your material balance, then you can write that in the more compact vector notation, and that's your state variable. So your state variables T and C are summarized or put together in the vector Y. So that's how we get to that general form. So I hope that answers that question. Please email me again if it's still not clear. And then let's look at this example. So we've got the tank here being fed with A and B, and it looks like they're in the same stream Q in, and their concentrations in the stream are Ca in and Cb in. The tank is perfectly mixed, and the exit flow rate is Q out. And so it's not saying here that these flow rates are equal. So generally speaking, we have to respect that the volume may be changing, right? It doesn't say that it's in the gas phase or anything like that. So it could be a liquid phase, hence the volume may be changing with time. And we want to identify the state variables and the control variables. And we want to develop the mass balances. And in fact, I don't think I did the solution here, and I'm not going to do the full solution here. There is another example in the tutorial where it's done in detail, but let's just do something as an outline here. So we've got A and B fed in with Q in, so we can write the rate of change of the moles of A, so dN sub A dt equals the flow rate of A entering the reactor is equal to Q sub in C sub A in, and then it's perfectly mixed, so we assume that the concentration in the exit stream is Ca, which is the same as the concentration in the reactor, and then A is reacting, so plus the formation rate of A. And what is the expression? So it doesn't say much about the reaction expression, so we can just leave it like that, and so that's general, but maybe we'll propose something just now. So now we also need to write this balance for B as well. So we can write the rate of change of moles of B. And of course here we are writing again on the entity. So the entity is the reactor. So this is the rate of change of the number of moles of B in the reactor. So that's a state that we can define. And here, then we've got some flow of B into the reactor. We've got B with its concentration in the reactor as well. And we can write the rate of formation of B here. And now, of course, we can see there's a state variable here. And we've got a state variable describing the similar thing here. So instead of this, we would prefer to write this as VCA, right? So the number of moles of A looks like that. And then if we expand this by the chain rule, by the product rule, then of course this would be C dV CA dV dt plus V dCA dt. Right, so now it's in the form that we expect, right? Or rather, now it's in a form where our state variable is represented in this way. However, we have this unspecified dV dt here, and we can't generally say this is a zero. And in fact, one of the students wrote to me about this problem, and I hadn't realized it was this problem. I thought it was the tutorial that I was being asked about. So in fact, in this problem, we don't have that Q in equals Q out. So, well, let me explain here what I mean. So if we write an overall material balance, if we write d rho v dt, right, that's the rate of change of mass in the reactor, and that's going to be equal to the mass flow rate in. So that's rho in Q in minus rho out Q out. Right, so this is the total mass balance across that reactor. Now, if the density is approximately the same, let's say that we know that there is reaction happening, so the way the moles are organized is going to change. But let's say it happens such that the density remains approximately the same. The mass density is approximately the same. Then rho will equal rho in will equal rho out. And so, and also if we regard that density as approximately constant in time, then that's a time constant. So we can imagine rho coming out here as a time constant, and then that density can cancel with these densities, leaving us simply with dV dt equals Q in minus Q out. So this is a kind of volume balance, so it's under that assumption of approximately constant density, and it's two assumptions really, that the density is constant in time and the density is equal across that reactor. If those two assumptions hold, then we can say this is true. And so looking here, we need to replace this balance in this way. We need to replace the dV dt part by this. By Q in minus Q out. And then of course we can process this equation further. We can take this across onto this side. So just shifting this across minus, right? And then divide through by the V. Right, so you can see you can divide by V here. Noting that V is not a constant. V is generally a time function, right? But still we can divide it here. And by the way, we have already preserved the fact that V is changing with time because we didn't zero out this term. So this term survives because we don't know whether these balance out. So that's why this term exists on the right-hand side. So this helps us preserve or respect V's time dependence. And so we can write it like this. And then we can, even though this is a time function, for every instant in time, we can divide by that current value for V. And so we can write dCA dt equals something. Right, so that's how we can get to the ODE that applies that applies in terms of concentration. So you can do the same kind of development for component B, and you then also have to add in this equation. So you will write the equivalent equation for B, and to get V as a function of time, to get V in its current value, you also need to be integrating this equation. So there are 3 equations we need to integrate in order to solve this problem. Okay, so that's how you work on this example 1. And part A, and in fact it doesn't ask us to go and solve those equations, it just says identify the state variables. So the state variables we found are concentrations A and B, and we have to also keep track of the state variable V, the volume. So we have 3 state variables, CA, CB, and V. In terms of control variables, as we said, we typically do that with flow rates. And in this problem, our flow rates, we have 2 flow rates, Q in and Q out. So we can definitely control the concentrations by varying those values. We can also think about influencing the inlet concentrations. So the inlet concentrations are the result of some, there'll be some feed, and in preparing that feed, there'll be some ratio of A to the substrate and so on. So we, if it is possible, if there is a good, or if there is a good level of control over the concentration of A and B entering the reactor, then those are possible other manipulated variables. And of course, there again, we could control those concentrations by changing the flow rates. So if there's some upstream mixing going on, if there's A and substrate being fed together and mixed somewhere, then the ratio of those 2 streams, we can change those flow rates. So through flow rate control, we can control the concentrations here. And then through more direct control, we can influence the total flow to that reactor. So that answers that question, the manipulated variables, it should say, for B. The required mass balances, we did that already. Okay, so that's example 1. And then in terms of solving for the time profiles, this is just a note for those of us who might want to justify how we integrate those equations, or what state variables mean a bit more. So we can see we are going to get this form dy dt, and then we can discretize this time-wise. So we can say, let's consider 2 different instances in time. Let's consider 2 different instants in time. So at time ti plus 1 and at time ti, we can define y to be yi plus 1 at time ti plus 1, and then yi will be y at ti. So we can say dy dt at, or in the range ti to ti plus 1, dy dt is approximately the difference in y divided by that difference in t. And of course, this becomes exact as this difference tends to 0. So that's what we have here. And then we can say, well, this thing is approximately the same as the function f. So if we take our differential equation, our original ODE, we have dy dt is some function of y and u. and of course, in fact, this is exact, right? dy dt is exactly equal to f of y and u. But here it's an approximation if we don't use y and u, if we use yi and ui. So that means we are saying that the gradient at some time, and that's a gradient that applies over a range, right, between I and I plus 1. In other words, the average gradient over that time range, that's approximately equal to the value of the function at one of those values. So if you imagine a curve, right, between I and I plus 1, there's some curve, and then we are saying that over that curve, the average gradient is approximately the same as the gradient that we get at one of those values, that is at the I value. So if we take that to be true, so this is a kind of forward difference, then we can approximate yi plus 1, right? We can say, well, if this thing is approximately equal to the value of f at I, then we can solve this for yi plus 1, right? We can just multiply this by this delta t and then add yi to that. In other words, we just solve for this part. And that's what you see here. So this is not intended to be a rigorous development of an integration scheme. It's almost like a mnemonic to remind us this is how we step forward in time. So if we have some current value for yi and ui, we can estimate what the next value of y is going to be. So this is how we step forward in time. And in fact, all our integration methods for ODEs work in this way. All our numerical methods work in this way. It's just that there are more sophisticated ways of estimating the change in y. So, and that's all it is. You'll hear many names. So Euler's method, Runge-Kutta, not Euler's method. Euler, not Euler integration, but there is an Euler name somewhere in there as a numerical approximation. Then you get Runge-Kutta, you get there are many. It's a subject of research for those interested in numerical methods, but all of them are just based on trying to get a good estimate for delta y, so that you integrate better. So it looks to us here, well, do you really need such a big field if you can just make this smaller and smaller and integrate forward? Well, some equations are not so easy. Some equations, sometimes you have many equations and they are highly coupled and highly nonlinear, and then more sophisticated methods are more important. Anyway, that's just reminding us how we can step forward in time and span out our solution. Here we are just specifying some specifying some values to the problem that we described earlier. So in this earlier description, in this example 1, we hadn't stuck any numbers to any of these things. Don't we still need something? We don't have the rate expression. Yeah, to really solve this problem, you need the rate expression as well, unless there's no reaction. Yeah, in fact, it doesn't say this is a reactor. It just says that A and B are being mixed in a tank. So you don't need a rate expression. You can apply these values. And just looking here, you can see that your Q in is greater than Q out. So in fact, this tank, assuming the density is about the same, this tank is going to increase in volume over time. You can see A and B, and here this is something I feel is explained right from the first year, but people always seem to have this confusion. The difference between the concentration at the inlet and the concentration initially. Now, contributing to the confusion is that some textbooks actually use Ca0 for the inlet concentration. So anyway, we'll talk about that just now, but let's go here. Right, in this picture, we should acknowledge that there are three different concentrations that we can think about. And here I'm not talking about A and B and C or anything like that. I'm talking about just one component. For one component, there are three concentrations we should think of. So first off, there's a concentration in the feed to that reactor, right? So, or that mixer, whatever it is. There's one concentration in this line. So in the fluid in this line, there's a concentration for component A here. And that is, generally speaking, different to the concentration inside the reactor here. And here I'm talking about some instant in time. So at some point in time t, there exists a concentration here, which we define as Ca, which is different to the concentration in this line here. So we are defining that as Ca in. That concentration is different to the concentration here. Generally speaking, it's also different to the concentration of A exiting here. However, if we can make the perfect mixing assumption, then the concentration in the fluid here is the same as the concentration in the line there. But there's no guarantee there's perfect mixing. It's not always the case. Sometimes it's the case that there's a significant delay in A exiting here, and that there's poor mixing in that process of exiting. So there may be some kind of bypassing or some kind of plug flow near the exit, and that gives it enough time to be converted to some value different to the concentration in here. So there is some other, generally speaking, there's some other concentration of A there. Now, that was not what I meant when I said that there are three concentrations. I said there's a concentration here, so I should say there are four concentrations. There's generally another concentration here. But the other concentration is the concentration initially in the reactor. So we can specify at some specific time, that is at t equals 0, that we can define a concentration in this reactor, Ca naught. So when writing this balance, where are we? We have to be very careful in what we mean here. Ca naught, that was the concentration in the reactor at time t naught. That's not the same as the concentration in the inlet stream to the reactor. And neither of those is generally the same as the concentration in the reactor itself. Right, this is the concentration in the reactor at a specific instant in time, right? At t is t naught. That's not the same as the concentration at time t. And that's not the same as the inlet concentration. And it's also not the same as the concentration at the exit point. So this is a problem and an error that I see over and over again. And as I say, I know that you feel this is obvious and I don't need to dwell on this much, but really from all the assessments that I mark and so on, this is an error that comes up again and again. It contributes to a confusion about what value refers to what stream. So this notation, I try to be a bit strict about the initial value, but some textbooks do add to the confusion by using Ca naught when they mean the inlet concentration. Okay, I went off on a bit of a rant over there, but in this problem we are given these numbers, and those are all the constants we need to go and integrate this equation. And we can just cut out the rates here. We actually don't have a reaction here. These are just kind of mixing vessels. So if you look at these equations, you actually are given now enough information to integrate this. You are simply given Q in and Q out at 12 and 10. So this is going to be on balance 2. So the volume in the tank is rising at 2, I guess, cubic meters or 2 liters per second. So it's accumulating at 2 liters per second. And so we can substitute dV dt is simply at 2 here. The concentration is the state value. We don't know what that is at some instant in time. But we take that across, and yeah, that's a 2. The Ca in is known, Q out is known, but we don't have this Ra. And this v of t, we can integrate that that equation, but because these are constants, we can actually integrate this equation quite easily and just say v of t equals 2t, right? It's 2 liters per second, assuming it was 0 at t equals 0. Then at some time t, it's just the 2 liters per second times the number of seconds, and then that's the current volume. So that would be the time function we could stick in here, and then we can integrate this equation for dCA dt. We can integrate that equation. Right, so that's how you solve that example. Then here, I do come back to differential equations at some point. It's one of the videos near the middle point of it's probably the third last video, and I talk about when we have two differential equations that are coupled. So here we read the left-hand side here as dx dt and dy dt, right? So we have dx dt, it's a function of x, but it's also a function of y. So x and y are unknown time functions. So when we integrate this, we start out with some initial value for x and y. And so x and y, if they are defined, then we just stick them in on the right-hand side. So we let's say we chose some value. So here I'm plotting the y versus x plane. So if we arbitrarily pick some point here, let's say we pick x equals -1 and y equals 2, let's say it was that point, then you have a -1. So for all the x values here, you stick in -1. For y, you stick in a 2, and then that will define some number, dx dt. Similarly, for y, we stick in x and y, and we get dy dt. And so that is going to be our the values that we use for the derivative that tells us in which direction x and y are moving. So they are either increasing or decreasing, and so if we've picked a point, let's say it was that point, then in the vicinity of this point we can say, okay, x is decreasing and then y is also decreasing, therefore my vector is pointing this way. So it's telling us the solution is tending to move like this on this plane. We are decreasing in x and y, so we are in general moving like this. And by the way, this is a nice bit of code that was written not by myself, by this is the p-plane code that was written for use in MATLAB, and you can see here that you can trace out all the solutions. And for this equation, it turns out that there's what we call a repulsor here. So it's a steady state, but it's not a stable steady state. So if you are exactly on that steady state point, there won't be a change. X and y will stay constant. But the moment there's the slightest deviation, then that solution will wrap around. If it deviates in this direction, if your x value were to increase slightly, then you'll be on this side, and there you'll have a positive dy dt and dx dt, so it will start increasing. Then you'll get to a point where dx dt becomes negative, and it will wrap around this way, and then it will fall into this steady state. And here, this is the opposite. This steady state is actually a stable steady state, and so we are repelled. That's why we use those terms: a repulsor and an attractor. So we are repelled away from that steady state and then attracted into this other steady state. And then if our values stray far enough away from this point, and if it falls in here, then there's yet another steady state. And this time, this steady state, in a way, is not so welcoming. There are quite a few oscillations. So our solution, I should be pointing this way, our solution will bounce around and it will spiral in slowly until we reach a steady state right here. So this system actually has 3 steady states in it. And And we need to be aware of that, right? The whole point of this course is about navigating such a plane, that we have some physical description of our system. We have some states, right? There might be concentration and temperature, for example. And when we have the wrong kind of combination between those two values, our system will tend to move away from where we might be intending to operate. It might move away from there and fall into other regions. And if we don't have a complete description of our system, it's going to be hard for us to develop a controller and, for example, avoid a region like this where the system is really going to bounce around quite a bit. There'll be quite a lot of oscillations before it falls into that point. So in the notes, the phase plane, that's what this thing is. We do introduce the idea here. There is another video, as I said, later in that series that delves into this in more detail. Okay, so that's the phase plane. Here we are looking at some of my own research where we noticed this phenomenon. So this is an example of chalcopyrite bioleaching. We found that we had a system with two stable steady states and one unstable steady state. And most of the industry, this was the iron leaching industry. So in that industry, they were happily operating in this region. And some plants reported that, on some days I managed to get this crazy high rate of reaction. And we were able to show that that's because the system has two steady states. And in fact, this steady state, which most people don't know about, you can accomplish if you can just break through this unstable steady state here. If you can force your ferric to ferrous ratio just high enough, then your system will run away and sit on this nice operating region, which is much better than the industry standard. So that's the kind of thing you can realize if you know about the dynamics. The reason I'm also showing this is because this is not just academic, right? There are intensely practical reasons for understanding our dynamics behavior. So it's not just interesting to me. It definitely is interesting to me to understand the phase plane of something like this, but it also has intensely practical outcomes and reasons. So towards controlling our process in the face of such complications, we in the real world go and build all this control around our system. And like we said earlier, in chemical engineering, the way we implement control is really by changing flow rates. And here's one. You can see 3 control loops here. And in fact, 2 of these control loops are trying to do the same thing, which is maintain the level in the tank. So there's a level transmitter here. So we need something that's going to measure the level constantly and feed back to the level controller. So there's some logic that is residing in some electronics here, and we've got some measuring device that's transmitting the current level there. And then you can imagine another line here where someone is trying to impose a set point. So they're saying, well, I want 1 meter in the tank, but you are telling me it's 0.8 meters in the tank. So there's some difference here. So that error is then used to drive the control action. So if there's this intended exit flow rate of water, we might actually close off this valve to allow this vessel to increase in its level to reach the set point. Same here, right? There's an oil exit stream here. So oil and water, right? So it might be we are trying to control 2 different levels in the same tank. So the oil level is being controlled here. And of course, you wouldn't try to control the water level with the oil outlet and vice versa. Well, you could, depending which one is sitting above which other one, but it's more effective if you try to control with the right phase. So that comes down to choosing the right control variable. Do we use the water flow here and connect that to the water level, or the reverse? So that's level control. Then out here, you've got a pressure control as well. And so pressure, that's of course in the gas phase. So then it makes sense to change the gas phase exit flow rate, right? You wouldn't want to try and control. You could control the pressure through the liquid level, but it's not really direct. And there are questions about if you leave that as a free variable, really it's going to become dependent on the exit pressure here. So here really you want to control the pressure by controlling the flow out here if the flow in here is a fixed value. So if you know the pressure here is fixed, then you can control the pressure in the tank through the exit flow here. So that's how we can read those flow diagrams and those really control diagrams. So this is just showing how level control is practically implemented. So the difference in those dip tubes and things like that, and that's some real equipment that's used to implement that kind of control. So the way we described it, we did it fairly intuitively, right? We said, oh, liquid or water level, yeah, why don't we use the water flow? And oh, pressure, yeah, from my chemical engineering knowledge, we should use a vapor exit flow. So that's not exactly intuitive. It's if you'll allow me to say, it's a kind of educated guess, but that's not the only way to figure out how to associate control variables. You can also you can calculate the sensitivity. So you can look at the data from that process and say, fine, I know the state variable is varying with time. But instead of considering the gradient of the state variable with time, instead, I could also differentiate it with respect to the control action. So I can look at all my data and look at, okay, when I was changing that flow rate, which variable was changing the most in response? So if you find, oh, that level changed a lot when I changed that liquid flow over there. So you can compute the sensitivity of each state variable to each control variable, and so establish then the strongest sensitivity pairings, and use that to determine your control approach. Excuse me. So that's how we can identify control variables. Then we will come back to this in detail. So we want to take some control action. We want to change a flow rate based on what the state is in the system. So for our example here, if there's a large difference between the set point and the current level in the tank, then we want to take more control action, right? We might want to, let's say the level was much higher than the level we wanted, then we might apply a high exit flow rate from here. And by comparison, when the two values are very close together, then we don't want to use such a high value. So the extent of the control action depends on the difference between the set point and the current value of the state. So the difference between the set point and the current value of the state, that we think of as an error. So the error between our intended our intended value and the actual value, that error should be used to drive how much action we take here. And so that's what we are saying here. We can define this error, so the current value of the state variable minus the set point value, that's the error, and we can base our control action on that. We can say my control action should be proportional to that error. And so that's a proportional controller, but the first kind of control here is a bang-bang control. And so that's when you have a control actor that can only vary between two states. For example, open and closed. So open is like a maximum flow rate, and closed is the minimum flow rate. So and this is a slightly more general, right? Instead of just saying open and closed, there's some maximum value and there's some minimum value. So if there's a positive correlation between the state variable and the control action, then if we are below the set point value, then we just apply the maximum value for the control, and then if we are above the set point, then we apply the minimum value. And so you can imagine that this will then get you to a desired state. So bang bang control, just you are bashing your way between two values until you get closer to your set point value. You can imagine very easily the drawback of this approach, right? Imagine when we do get to the set point value, your controller is, let's say you dip slightly above the set point value, then suddenly your controller is going to force it to this low value, and that's going to cause your y to drop. So then when it drops, then it forces it to that high value. So you can imagine this is always going to be jumping up and down. Your response will always be increasing and decreasing because you don't have very fine control here. So this is a very crude kind of control. Here, the proportional control, you can imagine, is much better. So we've talked about this, how that works. And then you also get other types of control. So if you have a difference, and let's say it's a small difference. So if you manage to get close to your set point, but you didn't get quite on that set point, right? If the difference was small enough, and if the control parameter you applied here was small enough, then you might not take much control action because there's not much difference here. But you see, that's not your intention. You want to operate on the set point value. So a way to cause the equation to become more responsive to a persistent small offset is to add up that offset over time. So if there is an offset that's persistent, then this integral will increase over time, and that will force the controller to take action. So we add that possible integral control. So you can see this is an integral action here. So that's how we can avoid. So we're getting fancy now in a way, right? We've gotten the major. We've gotten some kind of major control. This gets us pretty close to what we want to do. It's better than bang bang control. We accept through this we can probably get pretty close to the set point. And now we are really trying to cause the system to get very close to the set point. We are not allowing small differences to persist for long periods of time by implementing this. Right, so that's integral control. And then we can think, well, instead of waiting for error to accumulate in the system, what if I look at how the error is changing? So if the error is increasing, then I can extrapolate and say, well, the error seems to be increasing. I'd better take control action to mitigate that. And hence, we can think about applying our control action based on the rate of change of the error. And of course, if the error has that relationship, then this is going to be how we can relate the control action to the rate of change of the state variable. So we can add the so-called derivative action. Just that this does tend to cause a lot of instability in the system. So you can imagine if your state variable just undergoes a small blip, then that might cause a high gradient. Even a small change from 1 to 1.0001, that small shift, if it happens over a short enough time period, can cause this term to be very large. And so that might be a source of instability. So we have to be quite careful with this. We can control how reactive we are to that by controlling the derivative constant here. Right, and it says implement that. You'll see in the tutorial that we do this in quite a bit of detail. So we've said all this. You can read about this in more detail. This is just a hint that, well, if you want to avoid discontinuities and so on, if you just differentiate your control action, you can then account for time dynamics in your controller as well. Okay, so this, I guess, is now a reactor example, and we are given a kinetic rate constant, and we can control that. So you can look at that example. So in the first part of the course, you've done the Ziegler-Nichols tuning, and there is this the suggested recipe for accomplishing control for tuning those parameters. So that's all there. So Ziegler-Nichols tuning, you can read about that, but you've done it in detail in the first part of the course. All right. The code is here for that example. So example 1 and example 2, you can run this code. I can see the wrong value is used here. This should be at 10 and that should be at 12. So just check. Yeah, so you can see here the 3 differential equations are listed here, and so this is the general form. So you can use this code. You can play around with the numbers here, and this will give you the correct results. And yeah, this is written in MATLAB, so you can write it in MATLAB, or you can translate this to Python and you can run this code. I can see it is set up properly. So although here actually you need to modify these equations, so please update this. This is actually not correct, because we showed here that we need to include this term to account for the volume change with time, and so please include that term here, or you're going to get the wrong answers. Yeah, I might release the Python version of this with the corrected code a bit later. So that's it for this set of notes. I hope I've answered the questions that were sent by email like this, and